All right. Good morning.
Good morning.
So just some introductions for people who may not know you, or I guess me. This is Quoc from the Google Brain team. I guess would you say the AutoML team? Do you have a preference for one or the other?
I'm a member of Google Brain team right now. I'm collaborating and working in another team called AutoML. This is like a collaboration between Google Brain and Cloud and Google AI.
Oh, so you got a lot of different people you're talking with.
Yeah.
And then I'm Rachael. I'm a Kaggle data scientist. And this series is just like me sitting down and having coffee. I don't know if you have coffee. I have coffee with different people in machine learning.
Okay.
So the reason I wanted to talk to you is because I was really surprised at Next and Kaggle Days. So it was like 2 weeks ago, I think, at how well AutoML is doing. I'm just a little background on me so you know where I'm coming from. I've mostly been working in NLP where I haven't seen a lot of AutoML results that made me go like, oh, and I'm getting the impression that it's getting to the point where I might start be seeing more interesting work. So do you want to just sort of introduce the concept of AutoML?
Okay. One thing that I realized in the last couple of years is that although we claim to do machine learning, turns out most of the time the work goes in, first of all, writing the TensorFlow program or the PyTorch program to do machine learning. And even before that, you have to do some kind of manual work in terms of data processing and deciding what model you want to write the code for. And then after you write the code, you run the experiment, and well, you look at it and you say, maybe my learning rate is not very good. Maybe I should make the learning rate different. And it turns out that there's still a lot of manual work going on in machine learning. That's what I'm trying to say.
Yeah, absolutely.
Yeah, writing the code, data processing, and hyperparameter tuning. So upon that realization, what we want to do is to automate as much as possible some of the steps in that pipeline, really. For example, we proposed a couple of years ago the idea called neural architecture search, which basically automate one of the components in that pipeline, which is the architecture. For example, in neural net, it turns out how you create the architecture is very important, and it's very difficult. So we make an attempt to automate it, and we got some success, especially in computer vision. And recently we started working on NLP and tabular data.
So neural architecture search, my understanding is that it's been around for like a while, like as long as people have been working on neural nets. I want to say the 70s sort of is when it started coming up.
Yeah.
Why is it good now? Like what happened?
I see. Well, the most important thing, of course, is the fact that we have a lot more compute now than before. I mean, I still remember when I was in grad school, training a neural net takes like on MNIST take like a whole day, and now would take minutes.
Yeah.
And now with that improvement, well, doing 1,000 times of that neural net training is no longer difficult, right? And neural architecture search needs that. If your every model that you train take a day, and if you do it 1,000 times, that just means you need 1,000 days, and that's too expensive. Now you don't have that problem anymore. It's a lot faster.
Okay.
And that's probably the main reason. The second reason is that I think there's a lot more people have developed before neural nets pretty much vanilla, right? Like the LearnNet have a convolution and pooling, and that's pretty much it. I think now people develop more and more layers. A local contrast normalization, batch norm, and even convolution. We have depthwise convolution, and etc. So it becomes more difficult for us now to put things together, I would say.
The search space is bigger.
Yeah, the search space is bigger. So yeah, I think I would say those two main reasons. Yeah,
makes sense. So a question that I have, just sort of AutoML approaches in general, and I should clarify that we're talking about automatic machine learning or automated machine learning, the research topic, and not like AutoML, the product, which has the same name. It's very confusing. How sort of architecture general is it? So you mentioned you've done a lot of work on CNNs, and now you're moving more into NLP. Is it very easy to take the same approaches and apply them to, let's say, LSTM or transformers, whatever it is you're working with?
Yes. So I admit, so we haven't done like a great amount of work here to assess the transferability of these networks, but we done some work. For example, so my colleague Simon Conbliss, he took some of the networks found by architecture search, for example, and then he tried it on other data sets. And it turns out it does work very well. There's a correlation between good accuracy on ImageNet and good accuracy elsewhere. So
interesting. In the same domain, so still on images?
Yeah, the images. We're talking about just image recognition right now. Yeah.
Okay, so not like multitask stuff.
Yeah. So for example, if you have a architecture 1 and an architecture 2, and let's say architecture 2 is better than architecture 1 on ImageNet, and if you try it on Stanford car, you see that architecture 2 is still better than architecture 1 on Stanford car. For both, when you save the weights, even when you pre-train and not pre-trained. So yeah, so there's a correlation there. We recently worked on the another architecture called Evolve Transformer. So we take the transformer architecture and then we evolved it into a more sophisticated architecture, I would say. And then we tried on a number of applications in NLP, like translation and language models and so on, and dialogue generation. And it turns out that it also works better. It's still mysterious about why, but we saw some transferability. Although one of the key applications that we want is not just transferability, but for the current data set, what can you do to get the best? We believe that even when you have a massive amount of compute, that's always you should always do that. Try to optimize whatever it takes for your current data set of interest. I mean, at the third data point, I would say is that we work on this thing called MNASNet, which is a mobile-friendly architecture. We try to find an architecture that's small enough to deploy on a mobile phone. And it turns out that architecture does transfer for a lot applications. So the next generation of neural nets on the phones, I think, will be generated automatically. Yeah. But again, we talk a lot about architecture search, but I think there are certainly other components of machine learning pipeline as well, right? So a lot of the research coming from myself is about architecture, because I think it's interesting. The concept of architecture is very interesting, but we've done a lot of work on, hyperparameter optimization and data processing pipelines as well. And a lot of these things, same concept really. You want to find a good program, right? So this is symbolic. So maybe one thing that to break it out a little bit is neural net is very good for like the the backprop stuff, right? Like you learn the ways, but it's not very good with symbolic stuff, namely like a program that you need to create it. So you want to find that program, and that program might have data processing, architecture, and hyperparameters as well.
Interesting. So sorry to go back to the architecture search. I definitely agree that hyperparameter tuning and data cleaning, I certainly would like more automated help with in my work. So it almost seems like you're suggesting that there is a subset of architectures that for a specific family of tasks will sort of perform better across different tasks. And this makes me think of, so one of the constant conversations that's going on in the ACL world, the big NLP professional organization, is that part of what goes into writing a neural NLP paper is not actually in the paper. So it's like the specific, like the hyperparameter tuning. I've heard people refer to it as like the dark art of like knowing, just like because you've done it a lot of times, oh, these are the settings that are probably going to work well for this type of project. And it seems like to some degree, maybe, and obviously there's a lot more work to be done, architecture search might automate, and also maybe hyperparameter tuning, AutoML might help automate that process of like figuring this out by doing a lot of work as a grad student to the point where it's more, the machine does it. You don't have to spend 5 years doing, grad student optimization to learn how to write effective architectures.
Yes, that's true. And a lot of these things are kind of difficult to do it by hand and manually, and it's not that I would say it's interesting, but it's very tedious, right? Like for example, in the transformer, right? One thing that we know is that well, recently a lot of people use the transformer architecture. This is like the cell attention architecture for translation, let's say, right? And what they do is that they do translation one-by-one convolution. Attention. One-by-one convolution, attention, etc. You stack this up. So why is attention good? Well, attention good because it has some information globally. You look at the whole context, and you have a representation that kind of understand the whole context. But now, well, it's true that you have some hidden states that want to capture a global context, but that's too expensive because you might have some hidden state that just capture some local context, right? You don't, some n-gram or like a little window or something like that. So maybe you need some kind of convolution, right? You need some kind of small convolution that look at local context. But then the question is, where do you put the convolution and where do you put the global attention, right? So, well, if you ask me, I don't know, right? Like maybe I should put the local thing at the bottom and then put the attention at the top of the network. Well, sure, we can try that, but it becomes a lot of decisions to make. And I think automating that is better, and that's what we did. And exactly, it found something like the insight that I just mentioned. It basically put a lot of attention at the top of the layer, and it put more convolution at the bottom, so that it has local context, and then the attention will gather the information.
Sort of the way the hierarchical structure we think of for grammatical structures, where you have like local context and then it.
Yeah. So it's not way more different, more crazy like a lot of people think associate architecture search. But again, so that's one thing. The other thing is that a lot of people I think that architecture search right now is a total automation, which again is not true. But let me try to explain that a little bit more. So currently, when you do architecture search, there's a phase that you have to do, which is to define what called the search space. So you define like a search space. So you say, okay, you say transformer is good, but maybe I should create a search space around transformer. Right? So maybe the analogy that you want to see this is that instead of giving someone an architecture, you give someone a set of architectures. You want to give someone a set of architectures rather than the single architecture, right? Before, up to now, a lot of the research has done is in designing architecture is to give you one architecture. With architecture search, we're trying to find a set of architectures, right? A set of architecture, and in that set of architecture, the neural architecture search will find one optimal architecture for you, hopefully, right? So there's still a lot of work in designing that search space. So not total automation. The other thing that is not total automation is because a lot of the search is very expensive. We have to define something called like a proxy task, so that, like, you can eval very quickly, right? So let's suppose that English to French translation usually takes a few days to train, and if you for every model that you try, you wait for a few days, it's very expensive. So maybe we have to define like a little proxy task that you can evaluate within 1 or 2 hours. You can evaluate how fast, how good your model is, and there's still an art in defining this proxy model. So it's not total automation, but I would say the idea instead of giving people one architecture, we want to give a set of architecture, so which is essentially better.
Like, I'm pretty sure one of these types of models will be good.
Yes.
So I think you brought up a couple of the limitations currently. Yeah. So somebody needs to sit down and define what a good search space is. And I mean, that's going to take, obviously, domain knowledge and expertise. Yeah. You also mentioned designing a good proxy task is also very challenging. And I can definitely think of some ways that would go horribly wrong in NLP. Yeah. What are some of the other big limitations right now? So if someone's like, I want to use AutoML in my work, what should they be?
Yeah. So I would say those two are limitations, plus one more would be compute requirements. So right now, architecture search and AutoML in general is pretty good when you have a lot of compute. But when you don't have a lot of compute, it's a big challenge because you have to spend a long time to wait for the job to finish. I think I've seen recent very good research going on elsewhere, at MIT and other places that they try to develop MIT and DeepMind and Brain as well to develop better or more efficient methods for AutoML and architecture search. And it's pretty cool. You don't need, once you speed up the search, right? The key concept behind this is that they do a lot of weight sharing between networks. So when you create a new network, you don't start from scratch. You want to reuse information before, and that saves a lot of compute. And with that, you can speed up significantly, like 100 times. So that's something promising, I would say. But I just wanna, but it's still like research in progress. And I would say that one of the biggest limitations of AutoML right now is compute.
Yeah, that makes sense, because you do have to build multiple models, and there's really no way of getting around that.
Yeah.
And just a final question for me, because I know that you've mentioned previously about transfer learning, so taking one architecture you found with AutoML and the trained weights and then moving it onto a different problem.
Yeah.
I have the impression that some of the systems that say they're doing AutoML are doing like transfer learning and then like a little bit of architecture search on top of that. Is that the case? I don't know. I have not done a lot of reading in this area, and that's
we're still talking about architecture search and AutoML as research, right? Not a product.
Either.
Okay, so well, in product, then I would say we do both, right? Like it's silly just to do one, right? I mean, because both give you values, so let's do both. And turns out, yeah, both of them help. In a lot of research paper, we mostly focus on just architecture search rather than transfer learning. But we do observe that like a better architecture, when you have a better architecture in isolation, and if you pre-train it, it's also better than a worse architecture being pre-trained. So these two elements somehow kind of are two different factors. So if you add them together, you get the gains. So they don't cancel out. So which is a very good which is a very good thing. Yeah. So so that's a paper that I think we're gonna present at CVPR in this summer by my colleague Simon Conflith. Yeah.
Is there a preprint out for that yet?
Pardon? Yeah. You can find it on archive. The title is "Do Better ImageNet Models Transfer Better."
And that's to non-ImageNet data.
Yeah.
Sure, better. All right, I'm writing it down so I can remember to put a link in the, in the video when I upload it, so folks don't have to go Googling.
Yeah.
All right, thank you. This has been very informative for me. Before we wrap up, is there anything else you'd like to say to Kagglers as a whole?
Oh, so my feeling is so again, it's not yet. Okay. So one thing that I want to say is that AutoML to ML is like ML to no ML, right? So
just like picking
apparently machine learning is already a lot of automation inside machine learning, right? So the fact that you use machine learning is already automation of your process of designing a decision. So AutoML is basically a loop around ML to just basically say, here's a bunch of stuff that I don't know what would be the optimal values. Maybe do something about it to get even better values. So so I think it's a very natural progression when you have more compute. So I expect this would be a no-brainer to be used. Now the finding here during a lot of things that we do is that actually it adds a lot of values. Surprisingly, it adds a lot of values, more than people think. So that's surprising. But I think like compare no automation versus automation. Yeah, you should do automation when you have compute. Now the thing is that I think it's still there's still a human insights into this, right? First of all, designing the search space. And designing the proxy tasks and so on. There's still a lot of human insights going into this. There's still a lot of needed for expertise in machine learning and so on. The third thing is that we recently developed this thing called a mobile-friendly neural architecture with another team inside Google. And what we found is after we found a good architecture, we give it to some humans, and they look at it and they say, oh, it founds the architecture that look like this way. There's an insight here. So they build up on that insight and they improve the architecture. So that's a very fascinating experiment, and I think the future of like human and machine co-design looks very interesting. So that's something I think I'll see more in the future.
Definitely. And you're not going to put us all out of work and we'll be out on the street.
No, not yet.
All right. Well, thank you so much for joining me. I really enjoyed this. I've learned a lot.
Yeah. Thank you.